Good evening, everyone. Welcome to the session of JEE Bytes. On behalf of Meritnation, I welcome all of you. So, today we are going to start a chapter that's electrostatics. And in the class 12th, there's a first topic that you learn in schools. So, it's a very important topic as if you say from the point of view of JEE. So, hello Lavish, hello Braj, hello Wasim. So welcome to the session, students. Hello, Jyotsna. Good evening. Good evening. So, dear students, so today we'll basically talk about a very important law, that is Gauss's law. And we'll see some of the applications of Gauss's law. So, the first point that you should learn is electric flux. Electric flux. What is electric flux? Can anyone try? Can anyone tell what is electric flux? Electric flux. Electric flux basically means for a particular cross section, for a particular surface, the electric flux means the dot product of electric field and the area vector. Or we can say it's the number of field lines passing through a particular area, right? So wait a while, students. There is some technical error here. So wait a while. So first of all, we'll talk about electric flux. Okay. Electric flux is actually calculated as the dot product of E vector and delta S vector, where S vector is the area vector, okay, area of a particular surface, it should be like this, area vector, and this is the electric field at particular area, okay. So for example, if we say there is a cross section of area delta S, there's a cross section of area delta S. So the direction of the area vector will be the outward normal, okay, the outward normal for this particular cross section. So this is the direction of area vector, delta S vector. So suppose electric field is directed in such a direction that it is at an angle theta with the normal to this area. We say that the angle between the area vector and the electric field is theta. So in this case, we can say E dot delta S is equal to, let us say the area of this surface is delta S. So we can say it's E, magnitude of E, and delta S and cos of theta. This is actually the area. So this is actually the flux, the electric flux. Now, dear students, in this case, this delta S, this cross section or this area surface, it can be open, it can be closed. It can be open, it can be closed. Okay. So let's talk about the closed surfaces. For example, if you take a sphere, it's a closed surface. Okay, it's a closed surface, right? So Gauss's law states that electric flux through a closed surface is equal to Q enclosed by epsilon naught. This is Gauss's law, and it finds number of applications for like when you're preparing for JEE, a number of applications are based on this. So we'll see some of the questions based on this concept of electric flux. So in this case, students, this phi, this flux is from the closed surface. Okay, from closed surface. Okay. For example, if we consider this sphere, the Q in charge is a total charge enclosed in this. Okay. For example, let's say plus Q1 charge is there, plus Q2 charge is there. So Q enclosed will be the total charge that is enclosed inside it. Okay. The total charge. Okay. So this is a total charge enclosed. Okay. Total enclosed charge. So now let us see some application of this. A spherical shell of radius capital R has a charge capital Q spread uniformly over its surface. Which of the following graphs most closely represents the electric field ER produced by the shell in the range 0 to infinity? Okay. Where small r is the distance from the center of the shell. So dear students, we can see a very small derivation that we can have from Gauss's law. Suppose this black circle represents the shell. Okay, shell means a hollow sphere. Shell means a hollow sphere. Okay, so it's given that it's uniformly charged. It's uniformly charged. Okay, so let us say the radius of this be capital R, and we assume a Gaussian surface of radius small r. Okay. So in this case, students, you can understand that the electric field lines, they are directed radially outwards. And due to symmetry, the electric field lines, they are always perpendicular to a particular surface. Okay. For example, if you take a very small part of this Gaussian surface, so electric field will be perpendicular to that. Okay, electric field will be perpendicular to that. So we can say E is parallel to ds vector, where ds vector is a normal vector or area vector having magnitude ds, right? So we can say E ds for this complete sphere Gaussian surface is equal to total flux through this enclosed surface, right? So E dot ds. And now, as you know, the angle between them is 0 degree as they are parallel. So we can say E and ds and cos 0, and that's 1. So simply this is the flux. Now, see, electric field, it's constant. It's having the same value at the same distance, small r. So we can take it to be constant, and it can be taken out from this integration. So this means this is a total surface area of this Gaussian surface. So this means that's equal to E multiplied by 4 pi r square. This is the total flux, right? So total flux is equal to Q enclosed by epsilon naught. Okay, so E into 4 pi into small r square is equal to Q enclosed. Now, as a complete spherical shell is enclosed inside it, so we can say that total charge is equal to Q, the total charge on the spherical shell, divided by epsilon naught. So this means electric field is equal to Q over 4 pi epsilon 0 R square. Okay. So from this equation, or from this value of electric field, we can say that a spherical shell behaves as a point charge for the points lying outside it. Okay. So similarly, if you take the Gaussian surface inside the given spherical shell, so we can say, you see, E into pi r 4 pi r square. Now in this case, if you want to calculate the flux, okay, E into 4 pi r square. Let's say E is the electric field. Let's say flux to be like this. Okay, flux is equal to E dot ds. Okay, and it's integration. So we can see that, students, that no charge is enclosed in the Gaussian surface. So 0 upon epsilon 0. So this implies electric field is also 0 inside it. Okay. So inside a spherical shell, electric field is 0. And outside it, it varies as Q by 4 pi epsilon 0 R square. So we can see E is inversely proportional to R square for the outside region for R greater than capital R. So from this, we can easily see that the first one is the correct, because here you can see that electric field is 0, and outside it, E is inversely proportional to R square. So that's why the first one is correct. Okay. Now, if you talk about the spherical, you say a solid sphere. So in a solid sphere, similarly, we can find electric field for a point lying inside or for a point lying outside. How? Let us take this as solid sphere. And first of all, consider a Gaussian surface outside it. Let's take this a Gaussian surface outside it. So now next, see this. Let's take the radius of this to be capital R, and the radius of the Gaussian surface to be equal to small r. Okay. So this is the center of this sphere. So let's say rho is the charge density. That means Q by 4 pi capital R cube. Sorry, volume. That means 4 by 3 pi R cube. So this is the charge density. Okay, volume charge density, charge upon volume for this complete sphere. Let's say that the sphere is uniformly charged throughout the volume. Okay. So when you take the Gaussian surface outside it, same way you can say E into 4 pi R square is the electric flux. So we can say that E into 4 pi R square is equal to Q over epsilon naught, where Q is a charge over this complete sphere, right? So this implies E is equal to Q over 4 pi epsilon 0 R square. So from here also you can understand that for a particle, sorry, for a point charge, for a point lying outside this solid sphere, the solid sphere is actually behaving as a point charge. Okay. Now next thing, if you take this Gaussian surface inside, how we can solve it? When you take the Gaussian surface inside, let's take the radius of this Gaussian surface to be small r. Let's take it to be small r, and the radius of this sphere is capital R. Okay, so this is capital R. It's given that charge is capital Q. So there are two ways to solve it now. There are two ways to solve it. See, you can see electric field into 4 pi r square is electric flux, right? And that is equal to Q enclosed by epsilon naught. Now, what is Q enclosed here? What is Q enclosed here? You see, Q enclosed charge is equal to how much? It's equal to Q by 4 by 3 pi capital R cube multiplied by 4 by 3 pi into small r cube. This is the value of Q enclosed. Okay, how we're finding it? We can easily see that because the charge is distributed uniformly throughout the volume. So from here we can say Q enclosed is equal to Q small r cube divided by capital R cube. Okay, so this way we can say E is equal to, E into 4 pi r square, E into 4 pi r square is equal to, you say Q small r cube divided by capital R cube divided by epsilon naught. So this implies, now see from you, we can cancel r square and r from here. So we can see that E is equal to Q upon 4 pi epsilon naught r cube multiplied by small r. So this is for the points lying inside. Okay, for the point lying inside, E is proportional to small r. E is proportional to small r for inside points. Okay, and E is proportional to 1 by r square for outside points. Okay. Now, one more way we can say that E is equal to rho r over 3 epsilon naught. This is also the value of electric field inside this spherical, solid sphere, uniformly charged sphere. Okay. So, dear students, you can understand that the electric field is directed outwards, radially outwards like this. So, we can say that electric field to be like this. E vector is equal to rho into r vector upon 3 epsilon naught. So this is the value of electric field, okay, inside a sphere. Now next thing, let's see some questions over it. Charges capital Q, 2Q and 4Q are uniformly distributed in 3 dielectric solid spheres. 1, 2 and 3. There are 3 spheres, 1, 2 and 3, and their radii are r by 2, capital R and 2r. So if the magnitudes of electric fields at point P at a distance capital R from center 1, 2 and 3 are E1 and E2 and E3 respectively, then we have to find the relation between the electric fields. Okay, so you should be clear about this thing, that which formula to be used here. You see, for the first one, you can easily see that for the outside points, the sphere behaves as a point charge. Okay, as if the point charge is placed at its center. So E1 is equal to 1 by 4 pi epsilon naught divided into Q by capital R square, where capital R is the distance from the center, right? Similarly, in E2, we can say for even at a surface also, the same formula can be used, right? So E2 is equal to 1 by 4 pi epsilon naught into 2Q by capital R square, because the distance from center is capital R here. Now next thing, for sphere 3, now point P is lying inside it. So which formula to be used? You can use this formula. This formula you can use, this one. Okay. Directly you get the answer for this. So you can see E3 is equal to 4Q, the charge over it, and multiplied by small r. What is small r? The distance from the center. Okay. Now, in this case, the small r is equal to capital R divided by what? 4 pi epsilon 0 r cube. So in this case, this r cube, see, r cube was the radius of the complete sphere. Okay. So in this case, the radius will be 2r. So you can say 4 pi epsilon 0 divided by 2r whole cube. So from here, students, you can understand that E3 is equal to 1 by 2, 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught q by r square. So you can easily say that E2 is greater than E1 and that is greater than E3. And that is greater than E3. So that's why the correct answer is C. Okay. So I hope it's clear to everyone. Now let's see the other question. So an infinitely long, thin, non-conducting wire is parallel to the z-axis and carries a uniform line charge density lambda. It pierces a thin, non-conducting spherical shell of radius capital R in such a way that the arc PQ subtends an angle of 120 degree at the center O of the spherical shell. As shown in the figure, the permittivity of the free space is epsilon naught. Which of the following statements is or are true? So this question is a multi-correct type question. In this, there can be multiple answers. Okay. So how to solve this question, students? The first, let's read the first option. The electric flux through the shell is root 3 r lambda by epsilon naught. Okay. So first thing, electric flux. So we have learned that electric flux is equal to Q enclosed by epsilon naught. Because in this given situation, it will be very complex to find electric field and multiplying it with the area. It will have, a very complicated type derivation. So you can simply use the Gauss law. Phi is equal to Qn by epsilon naught. Okay. Gauss law can be applied in any situation, whether symmetrical, whether non-symmetrical. Okay. So Qn. So what is the enclosed charge? You see, inside the sphere, what is the enclosed charge? See, now PQ, only PQ is a line charge lying inside it, PQ. So in a question, it is given that this is P, this is P, and this is Q. And let's take the center to be O. So distance from O to P is capital R, and O to Q is also capital R. So by symmetry, we can say that this angle will be 60 degree. This angle is 60 degree. This is also 60 degree. So this PQ length, we can easily find that PQ is equal to 2R sine 60 degree. Okay. So from here, we can say that 2R multiplied by under root 3 by 2. So simply R root 3 is the value of PQ, the length of PQ. So how to find the charge? Q enclosed will be equal to lambda, that is the linear charge density, multiplied by length PQ. That is equal to lambda times R into root 3. r into root 3. This is the enclosed charge. So just you can find that flux will be equal to lambda into r root 3 upon epsilon naught. So that means the first option A is correct. Now, next thing, the Z component of the electric field is 0. Dear students, if you are talking about a linear charge distribution or a line charge, okay, suppose this is an infinitely long, wire of linear charge density lambda, and if it's having uniform charge density, the electric field will be directed outwards like this, okay, by symmetry, like this. So from on both sides, not on both sides, you can form a cylinder by this. Okay. So the Z component of the electric field is 0. But that's true because electric field is directed like this. It has no component in Z direction because this is Z direction. Okay. So it's perpendicular to that. So that's why B is also correct. So from here, we can say only A and B options are correct. The electric flux, we have calculated that, so it's not correct. The electric field is normal to the surface of the shell at all points. No, it's not possible. You can see that here, if you draw a normal, it will not have the same angle. Okay. So if electric field is normal to surface, that means the normal vector at the surface is parallel to electric field. Okay. So next thing, C and D cannot be correct. So only correct options are A and B. Now let's move forward to the next question. Consider a uniform spherical charge distribution of radius capital R1 centered at a region O. In this distribution, a spherical cavity of radius capital R2 centered at point P, where the distance OP is equal to A, and that's equal to R1 minus R2. So if the electric field inside the cavity at position is ER, then which of the following is the correct statement? So these are the statements given here. So next thing, students, first of all, you should know how to find the electric field in such type of configuration of charges. So first of all, let's take a sphere, a solid sphere. Okay. Now this is a solid sphere. Let's take O to be the point, the center of it. And let's take a point, let's take the point A at distance x. Okay. At distance x from point O. So in this case, you can see that the electric field at point A will be equal to rho x vector upon 3 epsilon naught. This thing I have told you earlier. Electric field at point A will be equal to rho x vector upon 3 epsilon naught. Now, this is the thing that we're talking about, a complete solid sphere. But when this point A is lying inside a cavity, but when this point A is lying inside a cavity, what to do in that case? Suppose we are going to find the electric field because of the charge in the cavity. Suppose cavity is also filled with the charge. Okay. Don't consider that it's a sphere containing a cavity. First of all, consider that this cavity is also filled with charge. Okay. So because of the complete sphere at point A, that is having a position vector to be x vector, the electric field is given as this. This is your point A. Okay. And now next thing, let's take this is the point P as center of this cavity. So if we are considering this as a part of this uniform solid sphere or uniformly charged solid sphere, we can see that the electric field at point A due to this other sphere can also be written similar way. Let's say this position vector be y vector. Okay. The position vector be y vector. So E due to small part of the solid sphere is equal to rho multiplied by y vector divided by 3 into epsilon naught. 3 into epsilon naught. So when this part is removed, how can you find the net electric field? Just subtracting them easily. Okay, just subtracting them. So now when there's a cavity, we can say that E net is equal to rho by 3 epsilon naught into x vector minus rho y vector upon 3 epsilon naught. So from here I can say it's rho by 3 epsilon naught multiplied by x vector minus y vector. So in the question it is given that a vector directed from O to P is vector A. It's an A vector. Okay. So if you talk about this triangle, you can see that this is O point, this is P point, and this is point A. So this is your x vector. This is your x vector. And this is your A vector. And this is your y vector. This is y vector. This is x vector. And this is A vector. So from this diagram, you can easily see that x vector must be equal to A vector plus y vector. By triangle law, we can easily see that x vector is equal to A vector plus y vector. So this implies x vector minus y vector is equal to A vector. So this means E net becomes rho by 3 epsilon naught into A vector. So it's a constant. You see the electric field has a constant value inside the cavity. It only depends on the vector directed from point O to point P. From O to P. So this means which other statement is correct? Only statement D is correct in this case. Okay. Because E is uniform and both its magnitude and direction depend on A vector. Okay. So thank you so much for being there, for attending your session, students. So to know more about Meritnation, how we can help you in your preparation of JEE, you can click on this link, and all the very best. And for information about AITS and our JEE Power Prep program, you can see the given link. Okay. So thank you so much, everyone. So all the very best.